Yes, good morning everyone. In the previous lectures, we have finished battery management system, and that too we are having two BMSs, right? First one is explained with the basic concepts, and the second one is exclusively for estimation of state of charge. Okay. After that, whichever we have used BMS for the second case, the same thing we are utilizing for the battery thermal management also. Okay. So today I would like to start with the battery pack thermal management. This belongs to the fourth module. Now here I will show how to model an automotive battery pack for thermal management task. So the battery pack generally consists of several modules, which are combinations of cells can be connected in series and parallel based on our requirement. And the module, each cell is modeled using the battery with the help of the SIP-scape electrical block. And the assumption is that initial temperature and the state of charge here, initial temperature and the state of charge are same for all the cells. So many cells we are using, every cell is having the same temperature and the same state of charge. That is our assumption here. And overall, cells together, combinations of series and parallel, we are connecting them and we are calling them as the modules. And again, the modules we are connecting them in series and parallel. At the end, we are calling it as a battery pack, right? So 8 battery modules we are using here. Out of them, 6 of one type and 2 of some another type. So, and those are connected in series to simulate a battery pack. So here 8 modules are connected in series, 6 are of the same type and 2 are of the different type. And the battery control subsystem defines the logic to determine the battery pack flow rate for the applied current load. So the battery is connected to some load. So whatever the flow rate that is required of the coolant, okay, so that will be decided by the battery control subsystem. So this is the overview of the model. So these example models of battery pack which is connected to an auxiliary power load. This is the auxiliary power load and this is the battery pack. Okay. So auxiliary power load from a chiller. So the chiller we are considering it as an auxiliary power load and it is defined in current sensor and auxiliary load. So all together this load we are considering it as a current sensor and auxiliary load. It's nothing but a pump. So the battery control subsystem, this is a battery control subsystem. It defines how much coolant flow rate is required to cool the HV battery pack. So this is the HV battery pack. So it will be heated based on your power requirement. This is the power load requirement. So that how much coolant is required to cool this battery pack is decided by the battery control system. So a controlled current source defines DC current demand from the HV battery pack subsystem. So this is a controlled current source. It will defines what is the DC current required, DC current demand from the HV battery pack. So you can see here, this is the DC power demand based on the load. This is load calculation and this is the DC power requirement. That is even with the battery control based on the present condition it will decide, right? I will show you the model here in the MATLAB Simulink. See, thermal management means current demand, ambient temperature and the coolant temperature. That are the inputs for the battery control. So battery state is also considered here and based on the present input values, what is the battery pack input is required, input data. So we are splitting the power, pump power and the current flow rate. Okay. So this will be given to the pump and this given to the DC here, current source. So that is the requirement of current based on the load connected. Okay. This is the battery pack. So is the overview of the battery here. The battery cell is modeled using the equivalent circuit model, and the equivalent circuit parameters used for each cell can be found in the installation file. I will show you. So here you will find the installation files. I will upload you this file BMS2, or else I will mention battery pack thermal management. Okay, these are the models. You will see the models here, and whatever the files that are required, that will be there here. Okay, mat files, simulink files, everything was there. Battery management system, battery pack thermal management, battery module, EV thermal management, all together, simulink and M files. So these are the models. So battery management system, battery pack thermal management, and EV thermal management. Okay. So the equivalent circuit parameters used for each cell can found in the .m file. .m files will also be there here in the resources. Not resources, sorry. Yeah, in the scripts data, you will see the M files or data files. Okay. Then how to build a battery pack? And to characterize a lithium ion cell, this example uses a 2 RC model. So the 2 RC model, RC equivalent model, I have explained in the module 3 also. Here no cell capacity fade or charge leakage is considered in this example. So it is a cell, it is not having any fade or no, no charge is leaking from the battery. So that is our assumption. So build a battery pack. How to build a battery pack now, right? So HV battery pack here is made up of the 8 series connected battery modules. 8 series connected battery modules. Module 1, 2, 3 and 6 to 8 are of the same type. So listen carefully. Total 8 modules we are using. Out of them, I have already discussed 6 modules are of same type and 2 are of different type. So in this 1, 2, 3, 6 to 8 are of the same type, with each module consisting of 3 parallel pouch type cells, 3 parallel pouch type cells for a series of 12 such strings. So this is the information regarding the module 1, 2, 3 and 6 to 8. So 12 strings are connected in series, and each string, 12 such strings are connected in parallel now. So 3 parallel type cells are there, and now module 4 and 5 are of same type, with each module consisting of 3 parallel cells here. 3 parallel cells per series, 16 such strings. So 16 strings will be connected in series initially, and each string, 16 strings we are calling it as a single cell now, and those type of cells are connected in parallel now again. So 3 cells are connected in parallel now. So all modules have same type of pouch cells, with the total number of cells in the HV battery pack is being equal to the 312. So how we are calculating this? Just I will show you here. So 6 modules, right? 6 modules of 12 to 3 cells. 16 into 3 cells. Okay. With each being rated of approximately 3.8 volts per cell. Each cell is being rated at approximately 3.8 volts per cell, and the total pack voltage here is close to 400 volts. So the different modules in the 400 volts HV battery pack are connected together using the bus. Okay, that I will show you now. Total 312 cells, right? In these modules, we are having 12 series. Here. Each cell getting 0.4 okay. So into 6 modules. So 270 stability. So this is for 6 modules. Whatever remaining 2 modules, there 3.8 volt cells connected in 16. In 16, right? So we will get 3.8 into 16, 60.8 volt here. So 16 cells connecting in series, and such type of cells we are having 2 modules here. This is per module. For each module, 60.8 volts we are getting. Thus, 2 modules. So the overall voltage we get here is 73. So all for 6 modules and 2 modules. Overall we have connected the battery is coming 3.6 approximately, and we are getting back. Okay. 1, 2, 3, 6 to 8. Total 6 modules we are having. So 3 parallel pouch type cells with 12 strings here. Okay. It was explained clearly. 12 into 3 cells. There 16 into 3. Total 216 here. Now, how these modules are connected? The different modules in this 400 volts HV battery pack are connected together using the bus bar modules. Bus bars modeled as a resistance. Actually, these are connected as with the bus bars here, but for designing Design purpose, we are taking the bus bars as a resistors here. We are taking the bus bars as a resistors here. See, lumped resistors we are considering. These are the resistors. The coolant flow mode distribution occurs in the pad with modules which were the module further away, it will receive the lesser flow rate, okay. So this is the battery pack. See here, module 1, 2, 3 and 6, 7, 8. 6, 7, 8 of same type, all those are connected in series. And each one is interconnected. The type of red color bus bar, certain specifications we are considering them as the lumped resistance, that is R02, R23, R34. Okay. So this is the structure of the battery pack now. I will show you what is the battery pack, what is a pouch type cells. Okay. Here we can see it is open. See, this is a battery pack completely. Module 1, 2, 4, 5, 6, 7, 8. Okay. And if you open module 1 again, see, this is the ambient temperature flow distribution to the different modules. Flow distribution. So it is further away, the flow will be less. Okay. This is the flow distribution to different modules R1 to R8 and S1 to S8. S means SOC here. S means SOC for each cell, and T is the temperature. So based on the SOC and based on the temperature only, the flow will be given, right? Flow rate will be given F1. F1 is the flow rate. So define battery controls. The flow rate calculation subsystem calculates a value for the input flow rate. So this is the blank flow rate calculation. Okay, flow rate calculation. This is a subsystem. It calculates the value for the flow rate. So it will give the flow rate here. And the pump power loss is calculated based on the flow rate. The pump power calculation is done here. The input for the pump power is flow rate again. And with 500 volts being the maximum pump power consumption, pump power is assumed to have a linear relationship with the flow rate here. So flow rate is here, pump power is here, both are proportional here. So after simulating these, so mainly battery control is depending on battery state, present state, what is the ambient temperature, and what is the coolant temperature now. So based on that, it will decide. Control system only, na? What is the SOC minimum and maximum limits, maximum temperature and minimum temperature limits. So based on that, it will check and it will decide the flow rate. It will calculate the flow rate required for each battery cell. Okay, flow rate required for each battery cell, and what is the total power requirement for the battery pack chiller load. Okay. So this, if you simulate battery pack thermal management, you will get this. What is the battery pack current required? Based on the load only, it will decide what is the pump power required, what is the present cell temperature, what is the present cell SOC. So those the decided step. Okay. So this is regarding battery pack thermal management. Battery pack thermal management. This is one topic on the module 4. So battery control system will be there, battery pack will be there, chiller load is there, battery control system. What are the inputs? I will show you here. What is the state, ambient, coolant, and it is giving as an input current, power, pump power, flow rate, and flow temperature. Okay, those are the inputs. So this black will calculate the pump power required. This black will calculate the flow rate calculation for each cell. Okay. This is a battery pack. And how to execute this model. So here in the models you will see battery management system. This is battery pack thermal management. This is the blacks which I have explained during this lecture, battery pack thermal management. Okay. Okay, I am stopping my lecture here.